Okay, so this is the prep video for section 5.2, integration by substitution. During the prep part, we're just really going to talk about basic functions and composite functions, and we'll hit the hard parts of the substitution in class. But I wanted you to get started thinking about the important piece, which will eventually be chain rule. So let's first start with this, integration of basic functions. We know three. We know the integral of x to the n would be 1 over n plus 1, x to the n plus 1, of course, plus c. This one would be ln, absolute value of x, plus c. And integral of e to the x is simply e to the x plus c. So these are the basic functions that I know. So let's look at a couple of different integrals, a few different integrals, kind of marching along in complexity, and then we'll see how that pushes us out of this category and into that category. So let's look at this one first. Let's look at the integral of 3x squared dx. You might recognize this as the exact derivative of x cubed, so the antiderivative would be x cubed. Okay, well what if I only have just the x squared? Well, that's no big deal, right? We just know to divide, we're going to raise the power and divide by. No big deal. We can handle that. Multiplying or dividing by a different number, that's okay. Same thing here. If we added a 5x squared, well, again, I'm not too concerned about the multiplying by a constant is fine. We can deal with that. That's just going to be 5 times whatever the antiderivative of that is, which we've already done, 1/3 x cubed. And then, of course, you would clean that up. 5/3 x cubed plus c. And you can go directly to here if you see that. Okay, so what about this one? 5 times x plus 7 squared dx. This was 5x squared. That's a basic, right? That's an x to the n. This one is not. It's not x squared, it's x plus 7 squared. Now, we could still do this one. We could just FOIL that out, no big deal. I'm going to pull the 5 out front. And then we'd have x squared plus 14x plus 49. Okay, so now those are all powers. So now this is a basic again. Okay, so multiplying by a different constant in the front, no big deal. Something like a square or even a cube, you can multiply that out. And again, then you get down to a series of basics. But what happens if you have this one instead? Wow, it is a polynomial. We could FOIL that out, right? 5 factors, because it would be a lot of FOILing, right? We could multiply all that out and then multiply by the 2x and the 6. We could multiply all that out, and eventually we would get a polynomial that would be all basic powers. But there is another way. So let's look at the difference between what's on this side and this set. This one had x squared, x squared, x squared. Just the x was squared. This one has x plus 7 quantity squared. So I can't work with it as it stands because this is not a plain x. It's a composite function. Same thing down here. This is not a plain x. It's a composite function, this function to the 5th. And in addition to that, I've got this piece over here. I can multiply by constants, that's no big deal. But multiplying by a function, that is a problem. So we need to think about how do we integrate composite functions. Basic functions we know, composite functions we need to look at. And so there are 2 things that we need to know. The first one is there is no reverse product or quotient rule. So we have product and quotient rules for derivatives, but there aren't any for integration. So we can't use that. But we do, let's review what chain rule is, because chain rule is something that we can work with. So let's consider chain rule. I guess I really only have just one thing I needed to say there. All right, so let's look at chain rule. Let's remember what this looks like. Chain rule says that if you start with a composite function, one function inside another, and we try and identify them as the inside function and the outside function, I guess exterior function. When we take the derivative of this, let me write it this way. When we take its derivative, We take the derivative of the outside, leaving the inside alone, and then we multiply by the derivative of the inside. So we have two pieces, the derivative of the outside and the derivative of the inside. Okay, so let's look at an example. So let's come back to, I don't know why I didn't make them the same. All right, let's look at this one then. If I wanted to find the derivative of x squared minus 7 to the 6th, I have a composite function. Here's my inside function, and there's my outside function. So first I'll handle taking the derivative of the outside. That's 6. Right, it's a power, so 6 times the inside to the 5th. So go ahead and drop that inside in. Times the derivative of the inside. Well, here's the inside. Its derivative is 2x. Okay, so if the derivative of this is this, if I start with, I'm running out of space. If I start with the integral of 6 x squared minus 7 quantity to the 5th 2x dx, if the derivative of this function is this, then the antiderivative of this function is this. So this one is that. So if I have a composite function to start with, and I have a full derivative, if I see that full derivative in the integral, I can do the antiderivative and come back here. So we need to talk about how do we, that's what we're going to talk more about in class. How do we make those connections? So let me do another couple of examples. And I think we'll clear that up. Okay, so let's look at this one. If I wanted to find the derivative, sorry, it's a little bit wet. If I wanted to find the derivative of e to the x squared plus 3, again, it's a composite function. Here's my outside function. There's my inside function. So its derivative would be, derivative of e to the x is just e to the x, so I still have this for my outside function, times the derivative of the inside, 2x. So what that means then is that if I start with the integral of e to the x squared plus 3 times 2x dx, this is the complete derivative of this. So this is the antiderivative of this, the same thing. So I can just write e to the x squared plus 3 dx, plus c, sorry. So the idea is we're trying to, based on chain rule, we've got the derivative of the inside, we have the inside, and we have the derivative of the outside. And so if we have all of these pieces, then we have the full derivative, which means we know, going back the other way, the antiderivative. So here, when I look at this, I see, okay, I have a composite function. This is my outside, and this is my inside. The derivative of this inside is right here. So in reality, I have all my pieces. What happens if I wrote this instead? Because this is how we more often write it. Is that any different a problem from that? And the answer is no, because I can multiply functions in any order I like, just like I can add in any order I like. So instead of multiplying the 2x on the back end, I can put it on the front end. It's the same thing. So when we start with one like this, it makes more sense, once we've identified the composite function here, to lump the 2x at the end. That's something we'll start doing because it makes it a little bit easier to see our way. So if I were to simply rewrite that then, well, I already saw that pattern. It matches my pattern. And so again, the pattern matching is what we'll talk more about in class. What if I had this one? Well, it looks awfully close to this. It's just that it's a 5 instead of a 2. And so, again, just like with basic functions, when the number's not quite right, we we can work with constants. Multiplying by constants, we can fix that. And so this again, we'll talk about this in class, how to fix this problem. So this is a how to fix in class. The important piece is the only thing that's wrong is the number. So again, when we start to look at these problems, the way we're going to start thinking about these is, I see I have a composite function. Identify the inside. If the derivative of the inside is here, more or less, or here, wherever it is in the order of multiplication, then I know I'm looking at a composite function that has a chain rule that I can work with. What is important is that if I have this, this is not one that we can do in this class. And why would that be? Well, again, I identify my composite function. Here's my inside. The derivative of the inside is 2x. The 2 is fine, but I don't have the x. And so the important thing here is that this we cannot do, not in this class, because we have to have all the variable parts. So let's kind of distill this down into a little bit of a process, and then we'll talk much more in class about how to handle it sort of formally. But the whole idea here is that what we're looking at is we're saying, I recognize that I have a composite function. So I have this e prime of I, an inside function. And if I can match this pattern, where the derivative of the inside is here on the outside, then I can begin to match this to the derivative I expect for this. And then I know that it will be the antiderivative. Let's see. Okay, so let's look at a process. And what you're going to hear me say in class sort of from now on is it a basic? Is it a basic? Is it a basic? By which I mean, take a look at the integral, and if it's formed of completely basic functions, you just do your basic integration. If it's not a basic, that's because it's a composite. And if it's a composite, then we need to look at this. So here's our process. First, we're going to identify that it is a composite. And once we know that it's a composite function, we need to identify which is the inside function. And so I, right, the inside function. And we need to identify the other parts. Because really, let's look at what we're trying to match. Remember, we are trying to match, the whole idea here is to match the pattern, derivative of the outside, times derivative of the inside. So, first thing we're going to say is, I identify it as a composite, I find my inside function, identify that, and then you're going to find the complete derivative I prime of x. And when we do it in class, we're going to use substitution, but for now, everything's going to match perfectly, so it's just a matter of beginning to see the pattern. Once we have completed that, then we're going to integrate just the e prime part. And that makes sense if you think about it, because think about chain rule. If I have this complete derivative here, then the only thing that I need to do is I need to find e, right? If I already know I, and I already know I prime, I know e prime, the only thing I have left to find is e, so I just need to anti-differentiate the e prime. Okay, so once we do this, so let's look at an example then. So I guess this is, if we're numbering steps, I guess it's like that. All right, so let's say we have this, 3x squared times x cubed minus 7 to the 5th dx. Okay, is it a basic? Well, we could multiply it out and make it into a basic, but we really don't want to. Instead, we look and we see, well, I see a composite function, and here is my inside. So I have identified the composite function and the inside function. What is the derivative of this inside function? 3x squared, So actually, I've got, this is my inside function, and this is my derivative of my inside function. And this piece right here is my E prime. So that means I have matched this pattern. And if it helps you to rewrite, since, again, we normally put the composite function first and the derivative second, please feel free. In fact, we will start doing this in class, particularly when we start doing the actual formal substitution, because it will make it much easier. We're just rewriting, we're just rearranging the multiplication order. So now we have our composite function, our I prime. So we have matched the pattern. So that means that we just only have to find E, and there's our E prime. So we'll have the inside function raised to the 6th divided by 6 plus C, stick in your inside function. Okay, I know this is a lot to think about. The important thing I want you to take home from this video is, one, we have basic integrals and composite function integrals, and we have to tackle them differently. For composite functions, we need to think about chain rule. For chain rule, the whole idea is we're trying to match this pattern. And so all the problems you have for your prep problems, you will have a complete I prime. So the pattern will match. It's just a matter of figuring out then which part is the outside function so that you can integrate that. Okay. So remember, once you have this complete I prime and what you're going back to, you just need to find the outside function. So again, we will talk about this much more in class, but I wanted to get you guys a running start because this is a hard topic. So I'll see you in class.